Okay. Hello, everyone. My name is Muhammad Abu Jafar Pikul. Um I'm an executive director at IT CPR, and I'm also Spintonics group lead. And again, I'm just welcoming everyone for public talk. So today's talk is plasmonic innovation, unlocking the future of light matter interaction. So, and this is our very first paper that has been published in Spinger from our photonic group. So today's speaker is Miss Nurain Amina. Okay, so without further ado, so yeah, go ahead.
Hello everyone. Assalamu alaikum. So I'm sharing my screen. The topic of our talk is Plasmonics and Beyond, Shaping the Future of Nanophotonics, arranged by Institute for Theoretical and Computational Physics Research. So our main focus is photonics today. So first question arises, what is photonics? So basically photonics is the science of light. It basically deals with the generation, manipulation, and detection of light. As we all know that light travels faster than anything in the world, so it's fascinating that we can manipulate it as per our need and use it in communication and different sectors. So light, what is light? Light is color and different wavelengths. And these wavelengths are made up of electromagnetic waves. And if we see more deeply, then these electromagnetic waves are quantum of photons. So talking about photon, this is the equation which calculates the energy of individual photons, which is different from one another. So now our work was focused on photonic crystal. So what is a photonic crystal? Here I have attached the cross section of a photonic crystal fiber, where we can see a pattern of cavity, which we call air holes, a periodic arrangement of air holes. So by analogy, if we compare it with a conventional material structure, which is a periodic arrangement of atoms, we are all familiar with this picture, where the arrangement of atoms changes the characteristics, the patterns of a material. In the same manner, in photonic crystal, using air holes, we make a definite shape which manipulates light to transmit through a certain path. So here at the center, we see a cavity which is called a defect, where light gets confined, because here the air hole, in the combination of air holes and the silica glass, a photonic band gap is created due to different refractive indices, and that is why light gets to travel into only a certain direction. So we can see a real life example of a photonic crystal, which is if we think of a butterfly which reflects different patterns, different colors, which is not only pigment but also due to the material pattern of its fin. So now, how does photonic crystals work? The basic mechanism behind photonic crystals is surface plasmon resonance. So how does this work actually? If we look at this diagram, here is a glass substrate, and over it there is a metal layer. So when light is incident on the metal layer, here is a region created, which is the metal dielectric surface. And when light falls on the metal dielectric surface, the electrons of the free electrons of this metal layer gets excited, which were already was in vibrational motion. So when light falls upon them, they get excited and starts oscillating together with a certain frequency, and the group of these electrons are called surface plasmons. So as these electrons absorbs a certain amount of a certain wavelength of light, so it creates a dark band which is detected by the detector. So this is the basic mechanism. So here is this is called the surface plasmon resonance angle. So due to the surroundings and different materials over the metal layer, it absorbs different wavelengths of light, and this line here shifts causing spectral shifts, and the change of the spectral lines, which we call wavelength sensitivity, is detected by our detector. Okay, so here I have attached a screenshot of our recently published paper, which is entitled Performance Analysis of a D-shaped butterfly core PCF SPR sensor for dual polarization guided by optimal gold tantalum pentoxide coating. So um, our main idea was to investigate the detailed analysis of our designed sensor for both X and Y polarization. And we also optimized certain parameters of our sensor to see how the structural parameters change affects the light matter interaction. Okay, so moving forward, we used COMSOL multiphysics for our simulation and MATLAB for graphical analysis. So our designed sensor here, this is the cross-sectional view. So we designed this D-shaped core where we created a hexagonal lattice structure of air holes. These are the air holes. So we structured the air holes in such a way that we created a cavity here so that light can get trapped into this region, and we have cut a D-shaped microchannel where we coated with gold layer, and as an adhesive layer we use tantalum pentoxide. So the main motto behind making the channel a D-shaped channel is to reducing the amount of gold needed and the amount of analyte needed. This region here is the analyte, meaning the liquid which we will intend to detect. So this is the lattice structure of our of the air holes and the silica glass, which can be fabricated through stack and draw method. These are basically cavity rods, and these are solid rods. Okay, so with thin and thick wall capillaries, we make this arrangement. And here is a 3D structure of our sensor. Okay, so the electrical field distribution, here is the picture of our simulation, which is from COMSOL multiphysics software. So the first picture right here, here we can see that light is confined into this region, making a butterfly-like shape. That is why we named a butterfly core. So this mode is called core mode. So mode is basically the certain patterns or definite patterns through which light travels. So when light gets trapped into this core region, we call it the core mode. And the second picture here, when light escapes from the core towards the metal dielectric surface, and here the surface plasmons couples with the photons, and as a result light gets trapped in this D-shaped microchannel. This is what we call the surface plasmon polariton mode. And lastly, the this is called the surface plasmon resonance mode. Here basically the phase matching condition occurs when the surface plasmon polariton mode and the core mode occurs at the same time. We get the surface plasmon resonance mode. Okay, so we uh, we studied the performance of our sensor for different layers. We tried different layers to see how the performance changes, how it reacts. So firstly, we used titanium oxide, then we used magnesium fluoride, and lastly, tantalum pentoxide. So after investigating the parameters like wavelength sensitivity, amplitude sensitivity, we got to see that when we use tantalum pentoxide, it it gave the best results. So here is the loss curves for titanium oxide, magnesium fluoride, and we also performed the simulation for without any overlayers, which is using only gold. Okay, so here is the graphs of when we use tantalum pentoxide as our adhesive layer material. So looking at the first graph, here we can see that the pink line is the core is for the Y polarized light core mode, and the blue line is for the SPP mode. So as I have mentioned earlier about resonance condition, so when does resonance occurs? When the core mode and the SPP mode intersects with each other in this region right here. At that time, the highest amount of light escapes from the core, causing resonance, and the loss is maximum at that moment. So this is the phase matching condition. And the second graph is the confinement loss for varying refractive indices. We performed our analysis for various refractive indices, and our sensor worked perfectly in the range from 1.34 to 1.42 refractive indices, and this is the total loss curve for all the refractive indices. Okay, and here we can notice one thing, that when the refractive index range is lower from 1.34 to 1.40 or 1.39, the variation is very less, and with the increasing of refractive index, the sensitivity of the sensor increases, giving better results. So parameters we studied here is wavelength sensitivity, amplitude sensitivity, resolution, detection accuracy, figure of merit, birefringence. And here I have attached all the highest values we got. Okay, so this is the linearity curve which determines the sensor's performance. Here we can see that in the x-axis, the refractive indexes, and in the y-axis, the resonant wavelength. So this is a exponential trajectory we notice here, that with the increase of refractive indices, the resonant peak wavelength keeps increasing, giving a progressive increase uh, in the peak wavelength. Okay, now this is the table of our key findings. Here is the refractive index range, which is from 1.34 to 1.43. For all of these, in this range, our sensor worked perfectly and gave optimal results. So for refractive index 1.42, we got wavelength sensitivity of 12,200, which is pretty good. But after that, we optimized certain parameters like air holes, the thickness of the adhesive layer, plasmonic material layer, and after certain optimization, we saw a significant enhancement in the result, and the best result was found when we increased the thickness of the tantalum pentoxide material to 25 nanometer, and the sensitivity enhanced to 34,000, which is huge. Here is a comparison with recent works. Uh, so this is our work, and this is all recent studies that we reviewed. Okay, so thank you. Feel free to ask any questions.
Yeah, thank you, Nourin, for wonderful talk. So I would like everyone to just give a like online clap for just cheer up, okay? And yeah, after that, if you have any question, just write your, just unmute yourself and yeah, ask the question. So any question from audience? So if not, I have yeah, one questions for you. So so just normal as understanding. So what are the main applications for the photonic crystal?
Okay, photonic crystals are used in like everywhere in sensors. When we walk through like a shopping mall,
Right.
the sensors,
Mm-hmm.
photonic crystal fiber is there. In lasers, laser light, photonic crystal fiber is there also. In these days, the applications in medical field has increased enormously for detection of cancerous cells, or any defected cells. And
Right.
so yeah.
Yeah, that's great. Yeah, there's a wide range applications. Yeah, I think Faria Tasnim has question. Yeah, go ahead.
Hi, Nourin. Nice talk.
Thank
Congratulations
you.
again for your first paper. I have a small question actually. So, how does the choice of metal influence the propagation length and the confinement of SPPs in your system?
Sorry, can you please ask the question
So,
again?
like the metals like gold, silver, aluminum,
Mm-hmm.
whatever you chose, like
Mm-hmm.
how did it affect your system?
Okay, so different materials have different properties. Here, the main factor is the refractive index of the material and how it interacts with photon. And so, when we change the metal layer thickness, the surface plasmon polariton, or surface plasmon, the amount of surface plasmons increased, and as a result the interaction increases, and that is how it interacts differently, and in a better or worst way.
Okay. Thank you.
Yeah, thank you for wonderful questions and answer. Okay, so anyone? Anyone from audience? Okay, so if not, then I have another question. So what will be your next project? Okay, I know this is very interesting topic. So what will be your next project or next goal?
Uh, we are working on that actually. We are thinking to add something new. We were thinking of fusioning actually with photonic crystals, how we can incorporate some new things, or how we can study some new characteristics. So we are working on that. I hope we'll um, fix something soon, but we didn't come to a conclusion yet.
Yeah, that's great. Okay. Okay. So overall, it's a very wonderful talk, and yeah, thank you for giving us the time from your busy schedule, and also, yeah, thank you so much. Yep. So yeah, okay. See you everyone then.